So now we're going to talk about the step-by-step process to calculate a chi-square and by hand. And then following a subsequent video, I will discuss about how to calculate the chi-square using Excel and what the actual results from a chi-square test mean. So a chi-square essentially is used to assess whether two variables measured at a categorical level are related. So we looked at a contingency table earlier, looking at survival and age group. So anything that can be put in a contingency table by categories is a variable that can likely be analyzed using a chi-square. Specifically, the chi-square tests are used to determine if the differences or relationships we see between two variables are due to sampling error or a reflection of a true relationship. So what we want to make sure is that anything we see by, say, the percentages are not exactly the same across several rows down a column, as we did qualitatively previously in the contingency table discussion lectures. Here we're actually testing whether those percentages that are different or potentially different are truly different, or if they're only qualitatively different, but statistically they're not different at all. So again, we need to consider a null hypothesis and an alternative hypothesis. The null hypothesis for the chi-square is that there's no relationship between the two variables in the population. And the alternative hypothesis is that there is a relationship between the two variables in the population. Now this is simplified, but this is more or less what you need to know for this class. The null hypothesis is that there is no relationship, and that the alternative is that there is a relationship. The chi-square test statistic is also written as an x with a square, with a squared notation at the top. So x with a 2 at the top. It's chi-square. The statistic measures how far a sample, meaning everybody you've interviewed, so you've interviewed 50 people in class from CSU MB and decided to see, I don't know, whether working a certain number of hours had enough impact on your GPA. You want to see how far that sample of 50 people is, how far it is from what we would normally see from a population with no relationship. So in other words, what we need to see is if we need to see the observed frequencies, which are the frequencies we've already calculated previously in the contingency table lecture, and we need to now calculate something called the expected frequencies. Okay? The observed frequencies are essentially just the numbers of people who fit into both categories. So a regular contingency table. In the expected frequencies, well, we'll discuss that in a second. The column percentages, if the column percentages are identical, we would normally assume that there's no relationship. And this is again, we talked about this previously. If you look down a column and the percentages are identical, we normally assume there's absolutely no relationship. So here's the steps to calculate your chi-square. Step one, you want to start with your observed or actual frequencies. These are absolute frequencies. This is looking at a variable of happiness, so very happy, pretty happy, or not too happy, and gender, male and female. And again, I have marginal totals here, 920, 1676, and 390. And that's simply 393 plus 527, 737 plus 939 is 1676, and 163 plus 227 is 390. And then I also have marginal totals for the columns. So 393 plus 737 plus 163 is 1293. 527 plus 939 plus 227 is 1693. And if you add up the marginal totals, either this way or this way, you'll get our total sample size of 2986. So if you add up all 6 of these cells, male, female, and then these 2 columns, but the inner cells, which we actually have the data cross-tabulated, they will add up to 2,986. So this is our observed or actual frequencies. Nothing is different here. These are the exact same type of data we've seen with the Titanic, survival and age groups, or gender and drinking coffee we saw in the contingency table lectures. Each cell in a contingency table will have the absolute frequencies, so that every one of these is just counts. These are called counts. So there's nothing, this is step one, and step one is essentially just to make sure that you have a contingency table, okay? So this is something you all can do very easily in Excel, and we'll again discuss this in the future. Step two is you have to construct a table with expected frequencies, which will reflect what table would look like if there were no relationship. Again, these are just absolute numbers. But if you remember in the contingency table lecture, we actually talked about how we can assess whether there's a relationship by looking at the percentages. We would look at, say, row percentages or column percentage. A row percentage would be 393 divided by 920, or 393 divided by 1293 would be a column percentage. So an expected frequency table actually is behind the scenes doing that same thing, but ensuring that the percentages either down a column or across rows are identical, okay? So, what it's basically doing is saying, okay, if there were no relationship between, say, gender and happiness, then the percentages will be identical, okay? So these are theoretical numbers. Here I've calculated, these are expected frequency cells, and the way you calculate them is you multiply the row marginal, here say 920 for the selected cell. So I'm interested in very happy and male, okay? So it would be marginal total for row times the column total, 1293, and then you're going to divide that by the total number of cases in the table. So in other words, your total sample size. So in order to start off with step two, what you really need to do is have a table with only your marginal totals in your sample size, and these inner 6 cells empty. It's easier to just do it that way. So in order to calculate to get 398.38, I would have done 920 times 1293, and then that value divided by my total sample size. And then for female not too happy, for example, female not too happy, I would take the marginal row total, 390, times 1693, and then that value divided by 2986. And let's say male not too happy. What two values would I multiply then? I would multiply 390, not too happy, and male, 1293. So 1293 times 390, and that value divided by 2986. Again, it's the marginal row total for the selected cell times the column row marginal for that selected cell. So the marginal in this column, and the marginal for this row. So where these two intersect would give me my value that I enter. And your marginal totals, by the way, stay the same. So now that you've calculated your expected frequencies, which actually give you what you would expect to see if there were no relationship, now we need to figure out what that actually means in terms of the chi-square. So now you calculate the chi-square for each cell. You take the observed cell frequency minus the expected cell frequency, and then you square that value and divide it by the expected cell frequency, okay? So here I have 393, which was my observed cell frequency for male and very happy. The expected was 398.38, and I'm taking that value and I'm squaring it, and I'm dividing it again by the expected cell frequency, which is 398.38. So let me show you. I'm going to take the observed. This is my table for observed. So you could just put a title here called observed. It says right here observed. Observed data, so 393. And I have now my expected, which is actually 398.38. And I'm going to take both of those values, 393 minus 398.38, and I'm going to square it, and I'm going to divide it by 398.38. And that gives me a value of 0.0726, okay? So that is a chi-square value for this particular cell here. And you're going to repeat that process for all of the cells inside your contingency table. So for males and pretty happy, which is the next cell down, for males, pretty happy, I would look at here. Males and pretty happy, in this case, would be 737 is my observed. Males and pretty happy, right? 737. 725.74 is my expected. and I would take that 737 minus 724, or whatever those values were from those previous two tables, take that value and square it and divide it by the expected cell frequency for male and pretty happy. So I do that for all 6. And in step 4, I'm just simply going to add them all up. So 1, 2, 3, 4, 5, 6. I have 6 cells. I add them all up. And I get a statistic of 0.769. All I did was add up all my cells together, my chi-square cells, and I get a total of 0.769. So now what do we do with that? Well, the last thing we need to do is to look at the degrees of freedom. So the degrees of freedom for a chi-square are calculated by the number of columns minus 1 times the number of rows minus 1. And you need the degrees of freedom to reference the table of critical values. Okay, so degrees of freedom, long story short, is just a tool we use in order to actually look at critical values table. All right, so just understand degrees of freedom is complicated in theory, and but very simple to use. So what you need to know is the degrees of freedom for a chi-square is calculated by the number of columns minus 1 times the number of rows minus 1. So here it's number of columns minus 1, so 2 columns minus 1, and then number of rows, which is 3 minus 1. So 2 minus 1 times 3 minus 1. That equals 1 times 2, which equals 2. Okay? So 2 is the degrees of freedom we have. So what we have now so far, the 2 pieces of information we have, is a chi-square test statistic of 0.769 and a degree of freedom of 2. So what do we do with that? So now we look at the chi-square and degrees of freedom on the chi-square table. Okay? So you want to find the degrees of freedom row, go across the column with 0.05. This value gives you the minimum value your chi-square needs to beat in order to be significant. If your chi-square is less than the critical value in the table, then the p-value is greater than 0.5 and you cannot reject the null hypothesis. You have to state that there is no relationship between the two variables. However, as it's in number 4, if your chi-square statistic is more than the critical value in the table, the p-value is actually less than 0.05 and you can reject the null hypothesis and state that there's a relationship between the two variables. Now I know this is confusing, and we will try to go over this quite a bit in class throughout the semester. So let me talk about the chi-square. I'm going to give you an example right now. Okay? So in what we just had here was a chi-square test statistic of 0.769, and we have a degree of freedom of 2. So what that tells us is we have degree of freedom of 2, right? Degrees of freedom. This is a chi-square distribution table. We will have this posted on iLearn. The first thing you want to do is look down the column of degrees of freedom, and you see degrees of freedom of 2. So that's all we're concerned about, is this row here, degrees of freedom of 2, okay? And we see that 0.05 right here is the p-value at which we need in order to reject or not reject the null hypothesis. So what this is saying is that in order for us to be able to reject the null hypothesis, the chi-square test statistic needs to be at least 5.991, okay? At least 5.991. But if you look here, our chi-square is actually 0.769. 0.769. So 0.769 is less than 0.5991, okay? So again, the only column of data we're looking at for the chi-square distribution is this 0.05 column. So looking down only this column for everybody, no matter how many degrees of freedom we have, you're only concerned about 0.05. And in this particular example we used, we had 2 degrees of freedom. So we're only concerned about this value here, 5.991. What our value we found in our table was that the relationship between happiness and males and gender was described as a chi-square test statistic of 0.769. This is less than the critical value of 5.991. So if we go back to our slides here, So we find the degrees of freedom, go across the column of 0.05. This value gives the minimum value your chi-square needs to be in order to be significant. If your chi-square is less than the critical value in the table, and in this case it is for us, 0.769 is quite a bit lower than 5.559. The p-value is greater than 0.05, and you cannot reject the null hypothesis. So in other words, we actually have to state that there is not a relationship between the two variables. So for this example, we would state that there's no relationship between happiness and gender. However, if we had a chi-square, that was, say, a chi-square test statistic that was like 7 or 8, if we go down to degrees of freedom of 2 and 0.05 test p-value, and we have a 7 or 8, which is greater than 5.991, what that would state that there is a relationship, right? So what we would say then is that chi-square is more than the critical value in the table, the p-value is less than 0.05, and you can reject the null hypothesis. And you would state that there is a relationship between the two variables. Again, I understand that this is very confusing and mind-boggling, if you will, and we will try to walk you through this step by step throughout the semester. This is just step by step by hand, and then I'm also going to show you step by step in Excel and what those answers we get actually mean. And a side note, the validity of the chi-square is, in order for it to truly be valid, you have to have two assumptions. The sample must be a simple random sample of the population. And if you can't have any cells, you can't have any cells less than 5 cases. So unfortunately, in your case, for this class, for your projects, you're not going to be performing a simple random sample. And likely you will have some cells that are less than 5. So unfortunately, your assumptions are not met. But we're still going to perform a chi-square. But you just have to understand that your chi-square is actually not all that valid for your particular study. But that is just a caveat that you need to acknowledge in your report. Unfortunately, with a non-random sample that have small cells, there are very few tests you can actually perform. So this is just so you know, in the real world, you need a simple random sample and have to have a larger amount of counts within cells.